this time we'll prove Liouville's theorem. So let's state it. So the statement is very short. So every bounded entire function is constant. So that just means that every function which is holomorphic on the complex plane, so on the whole complex plane, is constant. And this bounded, of course, also, not just holomorphic. So if it's also bounded, it's constant. And so for the proof, so let's take two complex numbers, a and b, and f be bounded and entire. So that's the setting, and what we are gonna prove is that f of a is equal to f of b. So let's see. So at first we'll apply Cauchy's integral formula, so we can write f of a as 1 over 2 pi I, then the integral over some curve c, where a is inside of the curve c, and then f of c divided by c minus a. And we'll specify the curve c later. So let's see. So we want to prove that f of a is equal to f of b. So at first we take a curve such that a and b are inside of the curve. So we'll see later how we want to choose the curve exactly, but at first we see that we want to have a and b inside of the curve c, so that we can write it like this, and so that we have this in the integral. Okay, and now we can simply go on, so we can write it like f of c times c minus b minus f of c times c minus a, then we divide by c minus a times c minus b. And now let's simplify a little bit, so we get integral over the curve c, then f of c times c minus f of c times c, so we don't have to worry about that. So we get f of c times a minus f of c times b, so we get f of c times a minus b divided by c minus a, c minus b. Okay, so let's go on a bit. So we have a minus b divided by 2 pi, and then we have the integral over the curve c, f of c times c minus a divided by c minus a times c minus b. And now it's slowly getting time to think about how we want to choose the curve c exactly. So at first we'll not do this yet, but we'll first use that the function f is bounded. So we say that this is at most a minus b divided by 2 pi, then times c naught, where we want to have that the modulus of f of c is at most c naught. So that's this constant c naught, and then we want to have the supremum of the c in the curve, and then 1 over, and then there's, let's say we take, okay, now it's time to think about how we want to choose this curve C. So we choose it a circle around the origin of radius r. So C, let me write it here, as a circle around the origin of radius r. Maybe let me not yet put this r here. So we have C minus A times C minus B. And then we need the r times 2 pi. So that's the length of the circle. Okay, but we still haven't specified r. So we need this for this supremum to exist. So let's think about it. So maybe let me draw a little picture. So, oops. So we have, let's say, A, and we have a point B. And now if we draw the circle large enough, then we get that the distance of this point A is at least, so from the circle is at least r over 2. So let me write it. So we want r to be such that C minus A is at most r over 2, and also C minus B is at most r over 2 for all points on the circle of radius r. So we want to have that, so that we get an r squared in the denominator here. And so that's this. Wait, sorry, that's wrong. So we want this to be at least. So as we make the circle larger, so we want this distance here to be large in comparison to to the radius. So okay, and so let's see what we have now. So we have, this is at most A minus B. Let's, the 2 pi cancel out, then we have a C naught r, and then we have a 1 over r squared over 4. So the 4, well, it's not necessary to write all the star, but that's A minus B C naught times 4 times 1 over r. Okay, and now all we have to note is that if for r tending to infinity, this tends to 0, and also we have to note that this inequality is still fulfilled if we let r tend to infinity. So that's good. So because basically we are free to choose r as long as it's large enough. So we let r tend to infinity, and so we get that f of a minus f of b is 0. So we get that f of a is equal to f of b, and that's for all complex numbers a and b. So that's what we wanted to prove. So this function is indeed constant, as f of a is equal to f of b for all complex numbers. Okay, so that's it for today. Yeah, maybe one more note. You can also use Liouville's theorem to prove the fundamental theorem of algebra. And yeah, that's it for today. Thanks for watching. Bye.